I know. I promised I'd finish this Vellum series soon. There's been this one thing on my mind which I wanted to do forever, and it's implementing a technique that's been known from structural engineering. And short disclaimer, please do not use any other setup we built here for actual structural engineering. It's just for the sake of trying this out and for visual purposes. So the technique is called ESO, and ESO stands for Evolutionary Structural Optimization, sometimes also called the soft kill option, which are two weird and somewhat intriguing algorithm names, I think. What the algorithm does is it takes a so-called build volume or a domain, in this case this rectangular shape here, and in this case this is a standard test for this algorithm or any optimization algorithm in structural engineering. This block here rests on 2 points on these sides here and has a load in the center pulling down. And now the algorithm should optimize this whole structure so that it has, say, only 30% of its initial volume or weight, but still decently supports the load that's been put onto it. And you can see 3 different variations of an algorithm here, and this is the shape it spits out. Looks a bit counterintuitive, but when you think about it, this is kind of a really stable shape that can rest on those 2 endpoints here and support a load pulling down here at the center. And the way these algorithms work is they do what's called the finite element method. That means they simulate the forces within that given piece of a build volume. And for each step, they simply delete the point that has the least stress, which means the point that is structurally contributing the least to holding up these forces. And I tried building that setup when Vellum came out originally. However, there was a nasty bug that prevented me from succeeding, but now this bug has been fixed since a few Houdini builds. So let's head over to Houdini and build this. The first thing I want to do is set up my build volume, and for that I'm going to use a box. Drop that down, dive in there and set up a scale of the box. And I want it to be 2 in width and 1 in height. That's the standard dimension for this test problems that we're going to solve. So let's make it 0.8 by 0.4 meters. And in this case, I only want to solve a 2-dimensional version of this. So let's scale it to 0 along its z-axis. Next, I want to turn this volume into individual points. I'm going to use the points from volume to do so, although technically this is not a volume anymore. It still works. Let's dial the point separation to say 0.02, like that. And next connect those individual points using a connect adjacent pieces sub here that will set to connect adjacent points. And I had good results with setting the surge radius to 75% of what my point separation in here is. So let's just right click on that, copy this parameter and paste it as a relative reference in our surge radius here and multiply it by 0.75. And we can also lower the maximum surge points to say 20. All right, let's hook this up, which results in this kind of topology, which I could not have at least easily created out of a standard grid. So that's why I went this route here. Next, let's set up the resting points. So those corner points on which my build volume rests and the center point where the force is acting on the whole thing. Using a few group nodes, let's set these to point and call the group where we're resting pin, and I want to use the keep in bounding regions feature here, wire this geo in there, and then let's decrease the size of our bounding box and move it a bit down and to the side, like so. Copy this, paste it again, connect it and set the initial merge to union, and now move the center over to the other side. So we now have those 2 points here in one group called pin. Next, we're going to create a force group for the point where the force is acting upon. Again, groups up, set it to points, call it force, disable the base group, but enable keep in bounding regions wired up. And then again, let's scale down our bounding box to something really tiny this time and move it down a bit, like so that we only have the center point here in that force group. Finally, let's store the initial position of our points here in a rest attribute using the rest sub, which just basically copies over our current points position into a vector called rest. Now for our ESO algorithm, the evolutionary structural optimization, I want to run a Vellum solver to figure out the stresses in this mesh and then delete the point with the lowest stress level. And I'm going to do that inside of a sub solver, which is just going to drop down here and then dive in there. And the first thing I want to do in this case is drop down a switch so that only on the first frame we will be using the input 1, and on every consecutive frame we'll be using the previous frame as an input. In the switch, I'll drop down a short expression here, just checking if $FF, that's my current frame, is equal to 1. And if it is so, we shall switch to our first input, just on the first frame. Next, I'll give my point in the center, the one in the force group, an actual force pulling it down using a point triangle, which only acts upon the force group. And I'll create a vector attribute called force, which our vellum solver will automatically read as such, and let's have it pull down by, say, 100 units. Now we can already configure our vellum constraint. I'm going to drop that down, move it here, and just let it at the most basic constraint there is, the distance along edges. I could use others, but in comparison, distance along edges is rather cheap to compute, so it computes a bit faster than the other constraints. To this, I'm going to hook up a vellum solver, but in between, I want to add another point triangle in our geo stream here. So the leftmost stream in our vellum chain, which acts only upon the pin group, setting its mass to 0. So that they don't move, those edge points here. Now, in my vellum solver here, for this case, I don't need any kind of collisions. They just will be expensive to calculate. Also, I don't want any additional forces, so let's get rid of gravity because I already have that force acting upon my construction here. I don't want any kind of wind, and I also don't need external or self collision friction here. In the simulations tab, and this is where that nasty bug existed until very recently, I want to set my simulation type to quasi-static. And quasi-static just runs basically this amount of simulation frames and just outputs it without actually running those frames on the timeline here. So the output of this will be the same as if we had a vellum sim that ran for 10 frames. In my case, I want to output only one frame, the first frame of the simulation. Let's just check the Advanced and Visualize tab. And in the Visualize tab, I want to actually display my stretch stress here. And I can see something interesting happening here. However, what I need to do to get something that's truer to the actual stress that's happening in here, I need to increase my constraint iterations to maybe 1024. So now I'm getting something that already is a bit similar to those images we've seen in the paper I've shown you in the beginning when it comes to the distribution of stress. So let's middle mouse on this vellum solver here. And we have an issue here because there is no stress attribute on here that we can access. However, when we drop down a null and wire the constraint stream into our null and middle mouse on that, we can see there's a stress attribute on our constraints. So in our case, let's just use an attrib transfer to transfer the stress attribute from the primitives that are in the constraint stream onto the points that are in my geo stream. So in this case, the first thing I want to do is just transfer my primitive attribute called stress. And under conditions, I want my distance threshold to be tiny, so only the very closest primitives will be taken into account. Let's highlight this, middle mouse on it, and we can now see that there indeed is a stress attribute, at least on the primitives in my geo stream. However, we wanted this to be on our points, so let's use an attrib promote to promote our stress attribute from primitive to a point. And the promotion method I'd like to use here is sum of squares. So if multiple primitives use the same point, this point will get all the stress attributes that are on the surrounding primitives, but their squared values. And what that gives us is basically the fact that the stress cannot be negative. So we'll always have a positive stress value. This will be important later because we're looking for the point with the smallest stress value. And if there's negative stress, which would indicate a negative load, there's still load on that point. However, by squaring this negative stress first, it also gets into a positive value, which then our algorithm will not try to remove. All right, now we've got a stress attribute here on our points. What we could do to smooth out some of these simulation irregularities is append an attribute blur here, just running over the stress attribute for one iteration, but that depends a bit on the actual configuration of your geometry. Sometimes it yields better results, sometimes it doesn't. We will just let it switched off for now. In the vellum solver, under visualize, I will just disable the visualization for now, and instead drop down a color node to just colorize our points using the stress attribute to give it a gradient, a ramp. The attribute values are just a bit tiny here, so like this, and maybe colorize it like so. Now, in order to keep our pinpoints and our force point here from being deleted by our simulation, we could either exclude them through grouping or just make sure that their stress value is always really high, so our algorithm won't be tempted to delete them accidentally. Let's just do that, again using a point wrangle, which is set to run only over our force and pinpoint groups, and just set the stress attribute on those points to a rather high value, say 1 billion. Now, in order to find our point with the minimum stress value. Let's promote our attribute to a detail. So I want to promote my point attribute to a detail attribute, which is a single value. The original name is stress. I want to change its name to a new name and do not delete the original. The new name should be min for minimum, and I will use the actual minimum as a promotion method. So this will just promote the point attribute to a single detail value, and it'll just pick the point with the smallest value, or it'll pick the smallest value that's present in the points. Next, we have to actually find that point with the smallest value and delete it, again using a point triangle. And in our point triangle, we want to check if a certain condition is met. And the condition is if my stress value minus my minimum value is smaller than a really, really small threshold. So let's say 0 point, that's 6 zeros and a 1. And then we remove that given point, the point that we are currently working on. So coming in through the first geo slot, and it's the point with the PT num. Okay, we haven't gotten our min value here, so let's look that up. Float min equals to our detail attribute coming in through our first slot called min. Let's check. Well, maybe let's lower this threshold here even further, add another 2 zeros, and now we're there, where only these very edge points here get deleted. Also, what I want to make sure in here is, as I'm running the simulation through my Vellum solver, it could in some instances happen that these points here move around, because the Vellum simulation actually moves those points around. So let's use this wrangle here to also reset those points to their original position, so they are back at their original position when we run another iteration of this whole algorithm in the solver. So all we have to do, as we wrote out the rest attribute before, is set our position to our rest attribute, like this. And that should be all there is to this algorithm. So let's just append a null here, call this one out, highlight it, and head up one level. So this is our solver. Let's just maybe highlight it and let it run for a few iterations, and you're gonna hear my laptop whine. So let's just maybe skip to the end of this frame range here, 240 frames. And we can already see that's going to the right direction. Let's just increase our frame range a bit and skip a bit further. Okay, and although that looks a bit anemic, let's scroll back a bit. And we can see that looks very similar to the structures we've seen in that paper. Even more so if we use a copy to points and copy a bunch of spheres onto those individual points. Let's just scale them down before we do that. So now we can see a picture that resembles a lot what we see in those papers there. Again, in this particular case, I found the algorithm to get minimally better results when activating this attrib blur in between, so it doesn't need to weigh that much. And also, a nice thing about this algorithm is that instead of just using this 2D sheet here, by just setting up this box and giving it a bit of a thickness here, you can make this algorithm work in 3D as well and optimize away in 3D. The not so nice thing about this algorithm, in any case, is that it might not be the fastest thing on the planet. But my perception might be off a bit here, as I'm still traveling and working on a laptop, which is not as fun, to be honest, as working on a full-blown Houdini workstation. Nevertheless, there can be quite some interesting structures that you can achieve with this technique, and hopefully, if that laptop is not altogether that slow, I'll be able to simulate something for you this night and use this as an intro picture for this video. So that's a very hacky, very cobbled together version of ESO, or soft kill option, using the Vellum solver in the quasi-static mode, together with the SOP solver and a bit of VEX code. With this one, I'm seriously intrigued which kind of structures you guys simulate with it and optimize with it, and I'm really looking forward to seeing some artwork from you guys. So please, if you create something using that technique, just send us a link. We're always happy to see what you cook up. And until next time, it's cheers and goodbye.